Something is wrong with the center of the Milky Way. Not wrong in the way science usually means, a gap in data, a rounding error, a model that needs adjusting. Wrong in the way that makes scientists stop mid-sentence. Wrong in the way that rewrites what you thought you knew about the place you live. In 2022, a new image was published. It came from the MeerKAT radio observatory in South Africa, assembled over 3 years of data collection and processing, and it showed the heart of our galaxy in finer detail than anything produced before. The team that built it expected surprises. They were not prepared for what they found. Emerging from the noise again and again were structures that should not exist. Hundreds of them, thread-like, impossibly orderly, stretching across the most violent region of the Milky Way, vertically, deliberately, like something drawn with a ruler across the face of chaos. Up to 150 light-years long, 1 to 3 light-years wide, perfectly organized in a place where organization has no right to be. Nobody knows what they are. That's not a rhetorical flourish, it is the scientific situation as it stands today. These structures, called non-thermal filaments, were first discovered 4 decades ago. They have been studied, debated, and named. And the honest answer to the question of their origin is still, we're not sure. This is the story of what they are, what they might mean, and why the uncertainty itself might be the most important thing about them. To understand why the filaments are strange, you need to understand where they are. The center of the Milky Way sits 27,000 light-years from Earth. In astronomical terms, that's our backyard, and yet it is as alien as anything in the observable universe. The innermost region, called the central molecular zone, spans roughly 1,600 light-years. Within it, the density of gas, the temperature of material, and the velocity of turbulent motion are 1 to 2 orders of magnitude higher than anywhere else in the galaxy. The cosmic ray energy density, a measure of how energetically active an environment is 2 to 3 orders of magnitude higher. This is not a subtle difference. It means the galactic center is, by almost every physical measure, a different class of environment from the rest of the galaxy. The region contains vast complexes of molecular gas, around 20 million solar masses of it, dense clouds of cosmic dust, ionized plasmas, extreme ultraviolet and X-ray radiation, magnetic fields in constant turbulent motion. And at the very center of it all, Sagittarius A star, a supermassive black hole 4 million times the mass of our Sun. These conditions make the galactic center extraordinary for astronomers. They also make it notoriously difficult to observe. Visible light cannot penetrate the thick curtain of dust and gas. To see through it, researchers must look in other parts of the electromagnetic spectrum. Radio waves are particularly useful. They have the longest wavelength of any electromagnetic radiation, from a few millimeters to hundreds of kilometers, and those in the millimeter to tens of meters range pass through the obscuring clouds almost without obstruction. They are the key that unlocks the galactic center, which is what makes what was found there, using radio telescopes, so difficult to explain. In the early 1980s, a PhD student named Farhad Yousefzada was using the Very Large Array Telescope in New Mexico to map a section of the galactic center in radio wavelengths. He was interested in star-forming regions. He was not looking for anything else. But something kept appearing in his data. Narrow strips of radio emission were cutting across the entire survey area. They ran right through the regions he was trying to study, in the same direction, at what appeared to be regular intervals. His first assumption, the only sensible one, was that they were artifacts, errors in the imaging process, interference, something wrong with the instrument or the processing pipeline. He spent a significant amount of time trying to make them go away. They did not go away. Frustrated, he returned to the telescope and imaged the same area again, this time using a different frequency. The idea was simple. Genuine artifacts would appear differently at different frequencies, while real features would stay the same. He compared the 2 images at 4 in the morning. The structures were identical. This was not a glitch. This was not contamination in the data. The narrow strips of radio emission, perfectly linear, enormously long, running perpendicular to the galactic plane, were real. More than that, they were unlike anything Zada or anyone else in the field had encountered before. What he was looking at had some immediately striking properties. The structures were vast. They ran for 50 to 100 light years in length, while remaining only 1 to 3 light years wide, a ratio of thinness that had no precedent in any known astrophysical object. They appeared to dangle vertically above and below the central molecular zone. Some came in pairs or clusters, running parallel to each other at a strikingly regular spacing, roughly 1 astronomical unit apart, the distance from Earth to the Sun. The consistency of that spacing was by itself deeply unusual. When Zada checked the same region of sky in infrared data, there was nothing there. The filaments left no infrared signature. This told him something important. They were not produced by heated gas, they were not thermal emissions. Further measurements told him what they were producing: synchrotron radiation. Synchrotron radiation is emitted when electrons traveling at close to the speed of light are deflected by a strong magnetic field. The filaments were highly magnetized and filled with relativistic electrons. This raised an immediate and still unresolved question: what was accelerating those electrons? The emissions ran continuously along the entire length of each filament. This ruled out localized events, a nearby supernova, a stellar nursery, as the source of the energetic particles. Whatever was driving the electrons had to be something operating at a far larger scale. Zada called the structures non-thermal filaments and suggested they were connected to processes operating across the galaxy as a whole. He published his results. The scientific community paid attention, then waited for more data. The data did not come. The telescopes of the time lacked the sensitivity to resolve the filaments in greater detail, or find enough of them to run meaningful statistical analysis. Over the next 35 years, only a handful of additional filaments were identified and characterized. Some were given names that reflected their visual form: the snake, the pelican, the bent harp. But the mystery of their origin made little progress. A remarkable discovery had been made, and then, through no fault of anyone, it sat largely unresolved. That changed in 2022. The MeerKAT radio telescope is located in the Karoo Desert of South Africa, on a site chosen specifically for its radio silence. It is made up of 64 interlinked antennas, each a 13.5-meter diameter parabolic dish, spread across 8 kilometers of protected land. The full array was inaugurated in 2018, the product of 4 years of construction. Its location in the southern hemisphere is not incidental. The tilt of the sun's axis relative to its position in the galaxy means that the galactic center, the central molecular zone, Sagittarius A, the whole turbulent interior, sits almost directly overhead from the Karoo. MeerKAT has what amounts to a privileged line of sight into the place where the filaments live. Beginning after the array's completion, an international team led by astrophysicist Ian Haywood and including Zadi, now a professor at Northwestern University, directed MeerKAT toward a 6.5 square degree section of sky, centered on Sagittarius A. This region, roughly equivalent to the area covered by 30 full moons placed side by side, was divided into a 20-part mosaic. The telescope was directed to survey each tile in sequence, using L-band radio frequencies between 856 and 1,712 MHz. In total, the telescope spent 144 hours on target. The result was 70 terabytes of raw data. To put that in some concrete terms, it is equivalent to approximately 700 hours of 4K video. Processing it required a specialized technique called a difference of Gaussians, a high-pass filtering method that removes large-scale background noise while preserving fine structural details. It is, in essence, a way of making the subtle visible. What the filtering revealed was unlike anything that had been produced before. The MeerKAT image of the galactic center looks, at first glance, like something between a scientific instrument reading and a piece of art. It is almost impossibly detailed. Tendrils of emission, loops and filaments and bubbles, fill every part of the frame. Familiar structures, supernova remnants, star-forming regions, are visible in new resolution, and scattered throughout, clearly visible for the first time in their true abundance, are the non-thermal filaments. There were far more of them than anyone had anticipated. Where previous surveys had cataloged a few dozen, the MeerKAT image revealed hundreds, an order of magnitude more than all previously known examples, most of which had never been seen before this image was published. The sheer number transformed the scientific situation. Statistical analysis, the kind of rigorous population study that reveals patterns invisible in isolated cases, was suddenly possible. The results of that analysis were published in the Astrophysical Journal letters. They confirmed several things and raised new questions about others. All of the filaments are magnetized. That much had been suspected from previous observations, but the MeerKAT data confirmed it across the entire population. More than that, the magnetic fields associated with the filaments are significantly stronger than typical galactic magnetic fields, in some cases 10 to 100 times stronger. Synchrotron radiation is universal across the population. Every filament identified shows this signature. And there was a new finding, made possible only by having enough filaments to compare: the spectral index, a measure of how emission intensity varies with frequency, steepens with galactic latitude. In simpler terms, the filaments appear to cool as they stretch away from the galactic plane. The electrons further from the center appear older. This is a clue. If the electrons are older at greater distances from the galactic plane, that suggests the filaments are not static structures, but dynamic ones, pointing back in time to some energetic event near the galactic center that produced the electrons in the first place and sent them outward. The most significant candidate for that event was already visible in the same image. In 2019, Haywood-Zadeh and the MeerKAT team published a separate discovery: enormous structures they called radio bubbles. These are vast volumes of radio-emitting material stretching symmetrically above and below the galactic plane, forming an hourglass shape thousands of light years across, centered on Sagittarius A star. The current hypothesis is that they were created by a catastrophic outburst from the black hole itself, somewhere between 100,000 and 1,000,000 years ago. The trigger may have been a massive infall of gas and dust into Sagittarius A star, or a sudden intense burst of star formation in the surrounding region. Either way, the energy released would have been extraordinary, sufficient to drive galactic winds outward from the center, stretching and amplifying magnetic field lines as it went, carving out the enormous bubbles in the surrounding medium. If you look at the MeerKAT image carefully, something becomes apparent. Almost all of the non-thermal filaments are contained within the radio bubbles. They are not distributed randomly across the galactic center, they are concentrated inside the outflow structures. This physical association is significant. The cosmic rays detected within the filaments, the very electrons responsible for the synchrotron radiation, match the estimated age of the Sagittarius A star outburst, thought to have created the radio bubbles. They are, by this measure, the same age as the bubbles themselves. The picture that begins to emerge is this: a violent galaxy-scale outburst from Sagittarius A star drove energetic winds outward, stretching magnetic field lines in its wake. Those stretched field lines became the filaments. The electrons accelerated by the event were channeled along the field lines and, as they interacted with the fields, produced the synchrotron radiation we observe today. The filaments are, in this interpretation, the fossil record of a catastrophic event in our galaxy's past. Zadeh and his colleagues describe this formation mechanism as magnetized streamers in a cosmic ray-driven wind, but they were careful in how they presented it. The hypothesis is compelling and consistent with the available evidence. It is not conclusive. The authors acknowledged as much in their paper, and the scientific community has continued to work on alternative theories. A mystery with 40 years of accumulated questions does not yield to a single image, however extraordinary. At this point, a reasonable question is, why does any of this matter? Non-thermal filaments are striking, genuinely puzzling, and clearly connected to something important in the physics of the galactic center. But are they more than a curiosity? The answer, potentially, is yes, and the reason points toward one of the largest unresolved problems in contemporary astrophysics. Every large galaxy with a supermassive black hole at its center faces a version of the same problem. The central regions contain vast reservoirs of gas and dust. Left undisturbed, that material would collapse into stars at a rate far exceeding what observations tell us actually happens. Something is regulating star formation. Something is pushing energy and matter outward from the galactic center and into the surrounding medium, slowing the consumption of gas. This process is called galactic feedback. Scientists know it must be happening. The mechanism by which it happens is not understood. The MeerKAT evidence, non-thermal filaments contained within radio bubbles, both apparently connected to a discrete outburst from Sagittarius A, suggests that galactic feedback may operate through powerful but intermittent events. Not a steady trickle of energy, but periodic releases of extraordinary force, each leaving scars on the galaxy that persist for hundreds of thousands or millions of years. This is supported by something found far from the galactic center. In 2010, NASA's Fermi Gamma Ray Space Telescope revealed what are now called the Fermi bubbles, two enormous lobes of gamma ray emission extending 25,000 light-years above and below the galactic plane, for a total span of 50,000 light-years. They dwarf the radio bubbles by a considerable margin. The calculation suggests they were produced by an outburst from Sagittarius A with the energy equivalent of 100,000 supernovae, vastly more powerful than the event thought to have created the filaments and the radio bubbles, and likely far older. Together, the filaments, the radio bubbles, the Fermi bubbles, they suggest a history of intermittent, massive energetic outbursts from the heart of the Milky Way, events separated by vast spans of time, each powerful enough to reshape the surrounding medium, each potentially slowing the galaxy's star formation and preventing the kind of runaway consumption that would exhaust the Milky Way's gas reserves long before today. The non-thermal filaments, in this light, are not a footnote. They are evidence of a process that has shaped the galaxy we live in. The story is not finished. The trail, after going cold for 3 decades, has not gone cold again. Since the first full-array MeerKAT survey, similar filament structures have been found in other galaxies. The properties are strikingly similar to what is seen in the Milky Way. Their presence elsewhere suggests that whatever produces them is not a peculiarity of our particular galaxy, but a feature of a common underlying mechanism, something that recurs wherever the right conditions exist. What those conditions are precisely remains an open question. Resolving it will require better data than any current instrument can provide. MeerKAT is already a formidable telescope, one recognized by the Royal Astronomical Society for the quality of its radio observations. But it was designed with longer-term ambitions in mind. It will become part of the Square Kilometre Array, an international radio telescope project that, when fully completed around 2028, will have a total collecting area of 1 square kilometer, and will be 50 times more sensitive than any existing radio instrument. What that sensitivity will reveal in the galactic center is genuinely unknown. Structures that are currently below the threshold of detection may become visible. The relationship between the filaments, the radio bubbles, and the far larger Fermi bubbles, currently inferred from indirect evidence, may become directly observable. Zeta has suggested that the next major breakthrough may come from gamma-ray telescopes operating at even higher frequencies. Higher frequency imaging produces higher resolution, which has the potential to map the connections between these nested structures with a precision not yet possible. For now, the filaments persist. They stretch above and below the galactic plane in their hundreds, highly magnetized, filled with relativistic electrons, cooling as they extend outward, and carrying in their structure and their radiation information about an event that reshaped the inner galaxy before modern humans existed. There is a quality to the situation that is difficult to articulate without reaching for language that science typically avoids, but there is something worth pausing on here. These structures, orderly, thread-like, vast, are embedded in the most chaotic region of the galaxy. They emerged from violence. They are sustained by processes that are not fully understood, and yet they are measurable. Their magnetic field can be mapped, their electrons can be dated, their positions, their spectra, their spatial distribution, all of this can be recorded and analyzed. The universe produced them. We are now, slowly, learning to read them. That is where the science currently stands, not at a conclusion, but at the edge of what the available instruments can tell us, with better instruments being built, better methods being developed, and a set of questions that have been open for 40 years gradually coming into focus. The image from MeerKAT was, as Zeta describes it, a watershed moment. Not because it answered the question of what the filaments are, but because it finally gave scientists enough to work with.